Hi, today I'm going to talk about how to solve systems of equations using matrices. I'll start with a 2x2 matrix, then move on to a 3x3 system and explain the geometric consequences of the system's results. For a two-equation, two-variable set of linear simultaneous equations, such as ax plus by equals c and dx plus ey equals f, the system can be put into matrix form like so. And you can prove this is true by performing a matrix multiplication and equating the elements of each matrix. We'll let this matrix be represented by capital A, this by capital X, and this by capital B. So the matrix equation can then be reduced to AX equals B. Now we can rearrange for X. With matrices we cannot divide, but we can pre-multiply by the inverse, which means we can take A minus 1 and multiply it by the whole equation. Now, a matrix's inverse multiplied by the matrix A minus 1 multiplied by A will always give the identity matrix, which is the matrix equivalent of 1, where it represents a square matrix of any size, where all the diagonals are 1 and all other elements are 0. As a result, this reduces to Ix equals A minus 1b, and as I is the matrix form of 1, Ix equals X, so X equals A minus 1b. Here, X represents our matrix, or in this situation, a vector, which represents our two unknown variables, which means we can find our two unknown variables, our X vector, by simply calculating A minus 1 multiplied by B. Which means x equals a minus 1 multiplied by b. So xy equals a, b, d, e minus 1 multiplied by the matrix C, F. This calculation, therefore, gives us the solution to the system. So this is a generalized form with algebra, but if we had numbers, by computing this multiplication right here, we would find the values of x and y in our system, therefore giving us a solution. This will always give us a solution unless the determinant of A is 0. Geometrically, this means that these two lines are parallel and therefore will never cross over. If the lines are not parallel, however, there will always be a solution. Extending this into 3 dimensions, the same principles hold. Given a system of equations, ax plus by plus cz equals d ex plus fy plus gz plus h, ix plus jy plus kz equals L. So here we have a 3-equation, 3-variable system. Putting this in a matrix form, you would find A, B, C, E, F, G, I, J, K multiplied by X, Y, Z equals D, H, L. Taking the same principles, A, X equals B, you can find our value X by simply computing A minus 1 multiplied by B, which would be A, B, C, E, F, G, I, J, K minus 1 multiplied by D, H, L. Now, I covered how to take the inverse of a 3x3 matrix in another video, so this can easily be computed, whether on paper or even on a calculator, to then just give you X, or the individual values of x, y, and z. Now, this will only work dependent on the determinant. If the matrix A was singular, or determinant of A equals 0, then a solution doesn't exist. This could be for a variety of reasons. The planes might all meet at a single line called a sheaf. So if it's like that's a crude 2D representation of it. Wait, but no, actually, it would be that. Sorry, my diagrams are terrible. If the planes all met at something called a sheaf or at a line, then the system of equations would have an infinite number of solutions because every point along that line would be a valid answer for x, y, and z. Therefore, if it forms a sheaf, the equation is inconsistent with infinite solutions. The planes could also form a prism, like this. Imagine that these extend on for infinity, obviously. But if they met at a prism, then all three planes would never meet at a single point, only two, which would mean that there is no solution for this either. Or two or more of the planes could be parallel, or even all three planes could be parallel. These above cases are all different ways that the system of equations can be inconsistent. And we must also be able to calculate what type of inconsistency is displayed in a system. By looking at the system, simply by inspection, you can tell if some of the lines are parallel. Whether ax plus by plus cz equals d, let's take this as equation 1, this as equation 2, and this as equation 3. Simply by looking at it, if 1 is a direct linear multiple of 2, or so on, or any of these are linear multiples of one another, then we must know that the planes are parallel. And therefore you can automatically know what kind of inconsistency there is and that it won't work. If, however, the determinant is 0 and none of them are parallel, then either the system forms a sheaf or a prism, and we must be able to detect which one it is. We can differentiate between the two by forming two new equations. Take, for example, (3x minus y minus 6z equals 1), x plus 3y plus 3z equals 2, and minus 3x minus y plus 3z equals minus 2. Let's label these equations 1, 2, and 3. Putting this in matrix form, we would find that 3 minus 1 minus 6, 1, 3, 3, minus 3 minus 1 and 3, x, y, z, and then 1, 2, and minus 2. The determinant of A equals 0, so we know it must be inconsistent. And none of these are linear multiples of each other, so we know it's not parallel. So they must either form a sheaf or a prism. To find out, we're going to form two equations from the original by using one to eliminate a variable from the other two, like so. I'm going to say a new equation, 4 equals 1 plus 2 times 2. I'm going to say 5 equals 2 minus 3. Now this will get us 5x plus 5y equals 5, and 4x plus 4y equals 4 respectively. Sorry, let me circle that. Now, these two are direct linear multiples of each other. They can both reduce to x plus y equals 1. Therefore, this system of equations reduces to a system with infinite solutions, or where all planes meet along a sheaf. And if the results were otherwise, the system would instead be prismic.